morning, Oral Defense Committee and listeners. Thank you for participating. I am邓彥甫, a master's student in the Structural Division of NTU. Today, I'm going to introduce the flow vibration serviceability and using piezoelectric two-man stamper for vibration reduction and energy harvesting. And my advisors are Professor Zhongli Lai and Professor Lai Yong'an. And this is my outline. First comes the introduction, which will briefly cover the whole picture of this study. And then an assessment for flow vibration serviceability will be proposed. And in the third section, the optimal design of the piezoelectric two-man stamper or the piezo TMD in short will be introduced. And then an example flow structure will be demonstrated to verify the concept of the second and the third section. And finally, the conclusion will be shown to sum up the presentation. And first, the introduction. So, the background. The floors for sports stadiums and dance rooms often need the entire space for the human activities. For example, sports events or concerts. And so the floors are often built as lightweight and non-stand structures, and a low vibrational frequency and lowly damping behavior will be shown. When the natural frequency of the structure is very low, like the floors that is introduced, many induced vibration frequencies proposed by Beckman and Ehman thoughts in a range of 1.6 to 2.4 Hz may coincide with the natural frequency of the structure. It may cause resonance, and if the vibration exceeds the acceleration limit, the serviceability problems should be concerned. So there are common solutions: stiffening the structure and applying two-man stamper, or TMD in short. And applying two-man stamper may be a more simply way comparing to stiffening the structure. You just have to simply add on the two-man stamper to the structure to reduce the vibration. And the concept of the TMD is to tune the TMD to the natural frequency of the structure. And while the vibration of the main structure is transferred to the mass block, the damping device can dissipate the energy created by the motion of the mass. And TMD can be used in many scenarios. It can be used on buildings to sustain the load in horizontal directions, like the wind loads or the seismic loads. It can also be used for floors or bridges to sustain the vertical loads, like human walking loads or other human activity loadings. So, there are already developed piezo TMD models with different configurations. And the latest model proposed by Cho has an advantage. By placing the piezoelectric stacks in series with the stiffness, with the mechanical spring, without using the dampers, more vibration energy can be harvested. And Ho improved the model by adding a mechanical spring in parallel of the model. Therefore, with the additional spring, it is a fail-safe system. So, the piezo TMD concept of piezo TMD is to use piezoelectric materials to generate the mechanical energy into electrical energy. However, in Ho's study, the dimension of the piezoelectric stacks is too long. It is 19 meters, which may be unfeasible. Therefore, a pantograph mechanism is employed in this study to make the piezoelectric stacks a more ideal size. And the concept is to soften the stiffness by the pantograph mechanism. And therefore, the piezoelectric stacks no need to be in a standard shape. It can be arbitrarily modified as we have the total number of the piezoelectric stack. And also, with the outer frame, if the piezoelectric stacks fractures, like the picture shown here, it can still remain a fail-safe system. And the second section is the flow vibration serviceability. So when we are doing the analysis, the membrane, plate, and shells are elements that can be used. So membrane can sustain in-plane stiffness, while the plate and shell, the plate can produce flexural stiffness and the shell produce in-plane and the flexural stiffness. So when considering vertical vibrations, plates and shells may be suitable. So here is the governing equation of a plate, which excludes the orthotropy and in-plane forces, variable thickness, and the effects of large deflections, shear deformation, and rotational inertia and non-homogeneity. Here in this governing equation, the W is the transverse deflection, rho is the mass per unit area of the plate surface. The D is the equation in terms of the plate thickness, the elastic modulus, and the Poisson's ratio, while the P is the external force per area. So, in this study, the frequency of the flow structure is concerned. So we'll look at the free vibration first. And in the free vibration, the external loads are neglected. The transverse deflection can be represented as a shape function and times an exponential decay, which is the amplitude in terms of the time. And by solving these shape function by different boundary conditions, for example, the classical boundary conditions, the clamped or the fixed, the simply supported and the free, we can conduct a characteristic equation. And by arranging the equation, we can get the non-dimensional frequency parameter. When we get the omega here to the left-hand side of the equation, we can get the angular frequency. And by deciding the length ratio A and B of the plate and the boundary condition of the plate, we can get a table proposed by A.W. Lysa. And while we choose the modes and the length ratio of the plate, we can get the non-dimensional frequency parameter by the proposed table. And the assessment of the flow structures. The general procedures are started from getting the dynamic properties, and second, to simulate the force model, and then generate the responses under the force model. And last, we can check if the responses under the force model is suitable under the criteria. So the dynamic, first we'll get the dynamic properties. We can get the structural frequencies, modal mass, and modal shape by the finite element model and the modal analysis. And we can get the modal damping considering to the material and the finishing of the structure. So in this table, it is an example table proposed by Wilford, which is a suggested damping ratio for flow structures. So it is put it into three parts: the structural damping, the damping due to furniture, and the damping due to finishes. We add these three parts as the chosen values, we can get the total damping. For example, the composite floor in the following example, we choose a composite structural damping 1% value here, and then it is used as gymnastic, so 0% damping in the D2, and we exclude the damping due to finishing to be conservative. Therefore, the total damping is then added, and we can get the total damping 1%. And with these parameters, the mass, stiffness, and damping coefficient of the structure system can be derived. And next is the force model. And in this study, the human walking force is introduced. So a single person walking is the equation shown here. It is proposed by a static load and a dynamic load. and a dynamic load including 3 to 4 harmonic components. The next step, we want to generate a crowd walking force. And in this crowd walking force, it is a Fourier equation, like a single person walking. You just simply multiply the numbers of the people on the flow structures and multiply the reduction factor, which is due to the correlation between the motion of different people. And this is the simplified force. And another method to generate a crowd walking force is by random force. And in this random force, the natural frequency is a random values that is normal distributed in the average of the 2.0 Hz and standard deviation of 0.13 Hz. While the phi j here is the under uniform distribution and is in a range of minus pi and pi. And next is the serviceability criteria. And vibration levels in the serviceability criteria are often quantified in terms of the peak acceleration, the root mean square acceleration, and the root mean square velocity. And the peak acceleration and root mean square acceleration criteria are often developed by the ISO z-axis base curve for acceleration curve. And in this curve, we can see that the acceleration limit varies when the force frequency varies. Therefore, it may be inconvenient for engineers to identify the frequency of the force. A rather simply way to choose for the serviceability criteria is the limiting accelerations without considering the associated frequencies. The Bigman and Aman proposed a peak acceleration of 10% g, where g is the gravity for slabs, and this 10% g is for slabs designed for sport practice, music concerts, and dance. And the Canadian standard, the CB, proposed the peak acceleration as 5% g for a similar use for the floors. So the third section is the piezoelectric two-mass damper. And we'll introduce the piezoelectric two-mass damper from deriving the constitutive equations. So we can see the variables, the force F, the charge Q, the formation X, and the voltage V. So we first start from the constitutive equations of the piezoelectric stacks. We can see the parameters K as the stiffness, theta as the piezoelectric coefficient, and C as the parasitic capacitance. Assembling the piezoelectric stacks into the O stacks in the horizontal direction and the N stacks in the longitudinal direction. We can call it a piezoelectric device. And in this device, the parameters, the stiffness, and the piezoelectric coefficient and parasitic capacitance are therefore shown here. In the next step, we will put the piezoelectric device into a pantograph device. And in this slice, we can see that the variables with the substitute of PP is the variables of the pantograph device, and the variables of the substitute of P is the variables of the piezoelectric stacks. So we can see the length of the shorter arm, the L, and the longer arm, the capital L, is in the ratio of the scale factor S, and the S is smaller than 1. Therefore, by doing the force equilibrium and the compatibility condition, we can see that the input force, which is the force of the pantograph device, is therefore reduced by the output force. For the compatibility condition, we can see the XP is S times the XPP, which means the input is smaller than the output XP. It's larger than the output XP. And therefore, we can further derive the relation of the stiffness. The stiffness is softened with the pantograph mechanism in a ratio of S squared. With the pantograph device, we will next assemble a spring in series, and therefore the effective stiffness, effective piezoelectric coefficient, and the effective parastic capacitance is shown in the slides. We will finally do the equation of motion by adding a proof mass block on the spring and the pantograph mechanism. And the equation of motion is shown here. The two equations of motions are derived by the force equilibrium of the mass block and the equation of motion of the circuit. So, therefore, we can get the mechanical frequency in the first equation and an electrical frequency in the second equation. We can then add the piezo TMD system on an SPOF structure. So in the figure, the upper part is the structure, while the downward part is the piezo TMD system. The three equations of motion are derived. The first equation of motion is derived by the force equilibrium of the structure, Ns. And the second equation of motion is derived by the mass of the piezo TMD, Md. While the third one is the equation of motion of the circuit. We can then arrange the equation of motion into a state space representation. And the optimal of the piezo TMD, we have to decide the objective functions. So before the design of piezo TMD, the objective of the optimization should be decided first. Therefore, by proper output matrix, C and the fit through together D, proper frequency response function can then be obtained. Two objective functions are shown here. One is for the vibration reduction, which is to minimize the mean structure displacement. And the second is for energy harvesting, who's aiming to maximize the mean power of the system. And the H2 norm is derived under the assumption that the system is under an external random force with equal intensity at different frequencies. And in the design procedure, the direct search method is adopted. The direct search method is an optimization tool in MATLAB, and it searches for the minimum of the objective function in the prescribed boundary. Therefore, we are searching for the maximum mean power, while the direct search method is searching for the minimum. We needed to add a minus here on the objective function of the power so that we can find the system, optimal system for the